Okay, so can y'all hear me first of all?
I can.
Chill, bro. Hello?
Hello.
Yeah, I'm screwed.
I hear you.
Wait, let me go again.
All right, you join.
Who's gonna call? Ayan, I think Kamsi. There's 5 people.
Wait, could it be that like the audio is going like elsewhere?
Nope. You're audible.
They can hear you.
They can?
I can hear you.
Hello?
Hello? Yeah, you're good.
All right. I'm just gonna
Yes,
get
I can hear you.
okay. I couldn't hear that for whatever reason. I think my like computer volume wasn't up or whatever. All right, appreciate it though. We're just gonna get started. Um, First, thank you all for coming. Hope you're all doing good. This is part 2 of our reinforcement learning lecture series. I'm going to start with a bit of review from I guess last week. I'm going to go kind of fast through it because I've got like other stuff to get to. But please ask questions, and also just know that if you haven't seen last week's lecture, it's up or should be up on like the drive or whatever. Yeah, let's just get into it. So first, what is reinforcement learning, right? Reinforcement learning is basically just a framework for solving a decision-based problem. This framework includes a few things, right? It includes an agent, which sequentially makes decisions in an environment based on whatever state it's in. And this state is determined by the environment. So the agent will then take actions in the form of decisions and send those to the environment. And the environment will provide it with a reward based on the action it takes, as well as a new state that the agent will transition to. The agent will continue this process until it reaches what's called a terminal state. What that means is that there's no more actions to take from this state. So when this happens, the episode, which is basically the whole process from the start state to the terminal state, the episode will end. So the goal is that over time, over multiple episodes, the goal is for the agent to be able to maximize the cumulative reward, or also called the return, by taking the most optimal actions it can. So let's go into what an environment would actually look like with an example. So this example is a 3x3 grid, right? Where each space on the grid, each vertex, if you will, could be called a state, right? And each state is taken from a set of all possible states denoted by capital S. And the important thing with these states is that previous states don't really matter to the agent. For an agent to make a decision, it only needs to care about the state it's currently in. The previous states it took, or the previous states it was at to get to the current state should not matter. We also have actions, which are taken from a set of all possible actions denoted by capital A, right? These actions would be like in the form of the agent moving horizontally or vertically across these states. We also have rewards denoted by in function notation using R, where it takes in the state, the action, and S prime, so the future state after taking that action. Here we could define a reward as -1 for every possible action. We're going to use this moving forward. Finally, we have a discount factor gamma, and that's used to weigh immediate rewards over future rewards. I explained it a little bit more in last week's lecture, so please, feel free to refer to that. So what does the agent care about all of this? Yeah, I'm recording. Doesn't look like it. Yeah, bro, see the dot? Look at the screen. All right. So basically the agent the agent could keep track of something called a value or a value function. And this is basically some function that describes the expected return of every state, right? So let's say you're in this 3x3 grid world, and this 3x3 table to the right represents the value or the expected return of every state. Like if we look at this top left state in the blue, the expected return, if you were to move optimally, would be Raphael win. The expected return would be to, if you were to move optimally, the maximum possible return you could get would be -4. We could take that a step further by defining what are called Q values. So a Q value is a function that describes the expected return of taking action A from state S. So it's further differentiating, like if you have your value, it's further expanding on that by specifying what the expected return would be for every action in a state as well, right? So if we have this, like this, if we're just looking at this top left square in this Q value table, this -4 would be the expected return if you were to move right. This -4 would be the expected return if you were to move down, et cetera, et cetera. So the important thing to note here is that the value of a state is equivalent to the maximum of all Q values associated with that state across all actions A. Okay, that's just that's an important relation that I'm going to keep coming back to throughout this lecture. So let's go into what a generic value-based algorithm would look like, right? Basically, as I said, we're going to navigate through an environment from the start state until you reach a terminal state. At each state, you would take an action and receive a reward. And this is used by the environment to navigate you to the next state whenever you need to. And in a value-based algorithm, we're going to update Q value estimates. We can either update them at the end of each episode, so after we reach the terminal state, or we could update them after each step. And how we choose to update our Q values is a major factor in determining what kind of algorithm we're working with. But ultimately, you're going to stop once you reach a terminal state and go back to the start state. And then you're going to keep repeating this for multiple episodes with the hope that your agent will keep improving. So if we have this, how exactly do we take an action, right? If we're working with only value estimates or only Q value estimates, how do we take an action? Because we don't have something to determine that. And a pretty simple strategy to determine how to take actions in a value-based algorithm is something called epsilon greedy. The basic intuition is that at each state, most of the time, you're going to take an action that corresponds with the largest Q value, whereas some of the time, with probability of epsilon, you would select a random action. And this allows you to honor your Q values by moving in directions that you know are really good, but also explore potential paths that you may not have explored before. So let's look at an example of what this may be, right? Let's say you're at this the blue like circle, and your epsilon value is 0.1, right? Let's say you generate a random number from 1 to 100. If that random number comes up 11 through 100, that falls into the range that's outside epsilon. So you're going to move in the direction of the largest Q value. However, if the random number came up 1 through 10, that falls in the range of the epsilon, right? So you would then select a random action. That could be the action with the largest Q value, but it also could not be, or may not be. Okay, so that's just a simple action selection strategy that some algorithms are going to use, as we'll see. So that brings us to updating Q values, right? In the last lecture, I went through a few slides showing how we got this update rule, but I'm just going to show it to you for now to save time. So the basic form of this update rule is that your new Q value for a particular state in action is equivalent to the old Q value plus some step size times the quantity return, or the most recent return you got on your episode, minus the old Q value. So let's look at this last quantity to really see what it means, right? If our Q value for that particular state in action is really close to the return that we got, that would mean that this quantity approaches 0. So the whole equation would simplify to new value equals old value, right? And what that means is that we're estimating our Q values really well. So there's really no need to update them further, right? In contrast, if the Q value was like a completely garbage estimate, that quantity would be much larger, corresponding to a much larger estimate or much larger change for this Q value, right? So this is our goal. We're trying to get our Q values to approximate G, to predict G, and be like a good expectation of G. That's basically our goal, right? We're going to work towards getting our Q values as accurate as possible. So before we move forward, let's look at what G is, right? If G is our return, does that mean that we need to go through an episode and get what the actual return is, what the actual cumulative reward is before we can do any updates? Not necessarily. We can use what's called a temporal difference update rule. And this basically makes use of the recursive definition of G. And this definition is as follows, right? This is basically saying that your cumulative reward, your return, is the same thing as the reward you immediately get from moving to the next state, plus the expected return of the next state, right? So if you have your cumulative reward, if you have like, let's say you have like 100 different rewards that you're summing up to get your overall return, the overall return could also be written as that first reward plus the remaining 99, right? That's all this is saying. And this is actually a really nice way to express it because it's a lot more stable. To see what I mean by that, basically it's that it's less susceptible to actions that result in very poor rewards that could mess up the overall cumulative return for other states, And this update rule kind of prevents that because it enables all our predictions to kind of update together. Again, I went over this in a lot more detail in the previous lecture, so please take a look at that if you haven't. But let's see what let's use this update rule in an algorithm, right? If you recall, our update rule, our overall Q value update rule is this, right? And since we have a way to represent G, we can just substitute this in directly to get this update rule. Okay, but recall this update rule uses V of S prime. If we don't know what V of S prime is, because we're only working with Q values, what do? And the answer is that we use this important relation that I just spoke about a few slides ago. And that is that the value of state S is equivalent to the maximum of all Q values associated with that state across all actions A. And we can directly substitute that quantity into our update rule, right? So this final update rule that only relies on Q values and estimates G using recursion is called Q learning. So let's walk through an example of what a Q learning step would look like. So we're going to follow an entire episode, basically stopping at each state. So let's say we're starting at the blue dot, and this is basically the state we're referring to in our Q table, right? Now we take an action from this state according to our epsilon greedy policy, and then receive a reward from the environment. So our reward would be -1. And let's say from this state, right, we've taken some action according to epsilon greedy. Recall that epsilon greedy means that most of the time we take the action that corresponds with the largest Q value. However, as we can see here, we didn't this time, right? Because we took an action into the direction of the -7, whereas -6 would have been a better action, right? So here we're taking a random action, okay? And this orange square denoted by S prime, that's the state we're going to end up at following this action. So now we're going to figure out what A prime would be to estimate our return as per the update rule. On Q of S prime A prime is going to be this triangle, this corresponding to this. Why? It's because of all the Q values of state S prime, this guy is the largest, this -5, right? So this is going to be Q of S prime A prime that we're going to use in our update rule. So now that we have what we need, we're going to use the update rule directly to update what our Q value would be. And that would be just following pure math. This Q value used to be -7, so that's our old value, plus our step size of 0.1, I've just decided that arbitrarily, times a reward of -1, plus gamma, I've said is +1, we're just going to use that constant, and then multiply by Q of S prime A prime, and that's going to be -5, minus the old value, again, -7, right? I'm just plugging in numbers that I've already found, right? And once you do this computation, you see that the new Q value for this state and action pair is going to be -6.9, right? So that's what an update would look like according to Q learning. So the idea is that you would just keep repeating this for every single time you take an action across episodes, and ideally over multiple episodes, your Q table would converge to the most optimal Q table where you don't need to make any updates anymore. Yeah, does that make sense? Any questions so far? Again, it was a little quick because it was pretty much review, but if anyone has any questions, feel free. Cool. Okay, so I'm just going to move forward. Basically, where we left off last time was that all of our value-based methods like Q learning, whatever, it can't deal with continuous state spaces. Why? It's because it's a tabular algorithm. It involves storing a Q value for every possible state and action pair. If you can have infinitely many states, like if your state was represented by like a decimal number and you have infinitely many states, it's just not going to work, right? Because you can't assign storage for like an infinitely many things. So how do we modify our algorithms to deal with continuous state spaces? Well, we could introduce a neural network instead of a Q table to estimate Q values, right? And that would look something like this, where you input the state, and then you get multiple outputs, where every output is what the Q value would look like for every action, right? So if we go back to our grid world, we have 4 actions that we could take at any state. We could represent it like this, right? Your first output is your Q value for moving up from state S. Second is Q value for moving down from state S, et cetera, et cetera, et cetera, right? And we could use this directly in place of our Q table. Does this make sense? Cool. So let's see what this would look like if we just use it directly in place. Everything else is the same with Q learning. So as we normally do, we're going to follow an entire episode, stopping at each state. And then instead of directly taking an action, we first need to find the Q values. And we're going to find this by passing our current state through the neural network and retrieving what our Q values would be, right? This is basically like we're looking up, remember how we're looking up our Q values in our Q table with regular Q learning? This is just that, except instead of looking it up in the table, we're passing it through the neural network because our neural network is learning to predict Q values accurately. That's our ultimate goal. So let's say this is what our Q values look like, right? So from state S, if you were to move up, our first output, this would be -5. From state S or 0, 0, if you were to move down, our Q value would be -4. Like these are just values predicted by our neural network. Okay. Now using these Q values, we're going to do the exact same thing we did with regular Q learning. And that would be just taking an action following the epsilon greedy policy. Recall that epsilon greedy means that most of the time we take the action corresponding with the largest Q value. Sometimes we take an action that's completely random. So let's say this time we take an action corresponding to the largest Q value and we end up moving to the right, in the direction of the -3. We end up moving to the right, receiving a reward of -1. Okay. Now we're looking into how do we actually update this neural network. Recall that in regular Q learning, we just needed to find Q of S prime A prime. And that was all we needed to update our Q table, right? This is the Q learning update rule. But recall that we don't have an update rule anymore. We're representing our Q values using a neural network. And so this update rule just isn't going to work. So we need to somehow translate this into some things involving loss functions, backpropagation, stuff that you would do for neural networks. And how you would do that? Well, let's look at what a Q value actually means, right? By definition, the Q value of state S and action A describes the expected return of taking action A from state S, right? That's what a Q value is. So basically, in other words, if we want our neural network to predict Q values, we want our neural network to actually predict returns. We want it to accurately predict the expected return you would get from taking action A from state S. Does this make sense? Cool. So, it just so happens that we know how to estimate these returns, right? For any given state and action, we can estimate the return the same exact way as Q learning does, right? And this is using this relation that we had defined a few slides ago. So if we just use this directly, first we can find Q of S prime A prime by again passing this purple state S prime through the neural network, right? And let's say these are the Q values we get. Okay, like completely random. These are just the Q values we get. This is what the neural network knows as of now, what the Q values should be. Okay, now we can use these Q values to estimate the return of this episode. And that is by following this exact formula. The reward we got, so -1 plus gamma of +1 times the best Q value from state S prime, and that's going to be -5. So our return of this episode, our expected return is -6. This is basically saying that if we started at the blue state, right, and by taking this action, according to how the neural network performs currently, we would expect a return of -6, right? This is our ground truth, if you will. This is what we think will happen, okay? So we want our Q value for state S, right? This should be basically predicting this. This -3 should not predict -3. It should instead predict -6. Does that make sense? So that's exactly what we're going to do with our loss, right? Our Q value, which we hope will predict the expected return, we're going to compare it to what we're assuming to be our expected return according to the TD update formula. And let's say we compute MSE loss, meaning that we take the difference between them and we square it. It's a pretty common loss with machine learning. We can just take this loss, backpropagate this loss through the entire model, and then we just keep going over and over and over again. Right? Does that whole process make sense? Cool. Are they asking questions? I can't tell. Okay. Yeah, I can't tell. Yeah, feel free to interrupt if you have questions. What's up? Uh-huh. How does a neural network know what state to use for S prime? Yeah, good question. It's basically, it depends on the action we took, right? this action is determined by the Q values for state S, right? We're following an epsilon greedy policy. And what that means is that for any state S, if we have the Q values, we most of the time, according to some probability P, some probability epsilon, we're going to take the Q value corresponding with the largest. We're going to take the largest Q value. So our best action so far. Whereas sometimes we'll take a random action. So then we'll follow through on this action to get our state S prime. Does that, hopefully that clears it up. Are there any more? Cool. Okay, yeah, as I said, feel free to interrupt at any point if you have any questions. I can't like see the chat or anything, so. Cool, let's keep moving. So yeah, that whole process, that's pretty much our algorithm, right? There was nothing wrong with it. However, it can be improved in a few ways. So let's get into that. So the first point of improvement is backpropagation, right? How often are we should we actually do backpropagation? So let's look at what the Q learning update rule actually does, right? We're only updating the respective Q value for that state in action, right? If we're performing this update rule, only that Q value changes. Nothing else changes. No other Q values for any other states or actions change. But when we do backprop, we're updating weights for every neuron. That's just how backprop works, right? So if we're only updating the neural network one Q value at a time, meaning that if we compute the loss for one Q value compared to the return that we wanted to estimate, right? This is affecting our neural network's ability to predict other Q values because all of the neurons are changing, right? If we're when we're doing backpropagation, if we're changing all the neurons to better predict one Q value, right, that could make it worse at predicting a lot of other Q values. So this is just not going to work. This is a general problem with supervised learning. That's why batch sizes exist, right? So that's what we want to do here. We want to simulate a batch so that when we do backpropagation and when we update our neural network, the update is representative of multiple Q values. So our neural network is getting better at predicting everything, not just one Q value at a time. Does that make sense? Cool. So one way we can do this is by using what's called a replay buffer. So a replay buffer is basically just a table that stores our state, action, reward, and S prime, so our future state, for every decision the agent makes across all episodes, right? So over its entire training process, this is going to store every single decision the agent makes. So let's walk through what that might look like, right? If we start at the start state, the blue circle, right? S prime is going to look like this, right? 0, 0 as our S, action E, I guess corresponding to like east, R, reward of -1. As we said, we reward of -1 for everything. And S prime, the next state that we ended up at, right? If we were to keep following this, right, it's the same exact principle. State we started at, the action we took, the reward we got, and the state we ended up at, right? Same principle. And like on the next episode, if you were to move down, that'll just get added again to the end of the replay buffer. That idea makes sense? Cool. So now that we have like a log of all the decisions our agents taken, we can still perform backpropagation, where instead of only using one Q value, the Q value that should be getting updated, we're going to randomly pick several rows from this buffer and then compute the loss for all of them, and then use that to train the model. So we're simulating a batch of a bunch of Q values that the model has probably estimated and versus what the estimate should have come out to, and we're going to use all of those to update the model. So the model learns multiple Q values at a time. Okay, does that make sense? Why we need a replay buffer and how this helps? Cool. So we still have another problem or another area that we could improve. And so to introduce this, think about what we're using our neural network for, right? We're training our neural network to predict Q values by comparing it to the reward we got plus Q of S prime A prime, right? We're comparing it to our estimate of G as per the Q learning update rule, right? As per the update rule I discussed with TD, we want each Q value to get really good at predicting that, right? This is just like this. I'm just repeating stuff I've gone over in the past. That's what we're training our neural network to do. However, this value Q of S prime A prime, which is part of the the return estimation, that is also being predicted by our neural network. So we're effectively training our neural network to predict something that it also predicts, right? Think about how a neural network is trained like with a regular supervised learning problem, right? You have your inputs, you have your outputs, or you have your like expected labels, your answers, and those labels never change, right? They're fixed. The goal is to get your neural network to predict those labels as they are. Those labels will not change, but they're clearly changing in the way we've set this up, right? Because as we keep updating our neural network to predict the Q of S comma A, we're inadvertently changing our prediction of Q of S prime A prime, right? That's just how the neural network works. So our current setup, we're having our neural network predict values that will continuously move as the neural network keeps changing. It's having it predict like a moving target, right? Think about how that's problematic, right? That's not what a neural network is set up to do. So this generally introduces instability. Does this problem make sense? Yeah.
So like currently, in this example, would the neural network not really have any like meaningful updates until it reaches the goal at least once?
Yes, that's something I kind of just hand waved. A replay buffer isn't really useful until until you have enough values. That's usually when you reach the goal at least once. Yeah.
Okay, because like initially all the values are just like randomly initialized.
Correct.
And then you don't really know how to update them according to the ground truth, so to speak, until you reach the goal.
Exactly. Yeah.
Okay.
That's why, again, why it's really unstable, because they're random initially. So you need some semblance of a goal in order for them to improve and then further improve on top of that. Yeah, great point. So a solution to this problem is to use two neural networks, right? One to predict Q of S comma A, and then one to help estimate the rewards with Q of S prime A prime, right? These are going to be trained on exactly the same data. So for they're going to be very, very similar. But the only difference is that our second neural network to predict Q of S prime A prime to be used with return estimation, that one will be trained less frequently than our first neural network. So the idea is that our values, our estimates for Q of S prime A prime, they don't really change as much. They will still change and improve over time, but for a few steps at a time at least, they won't really change. So you have some semblance of a goal with which to compare your Q value estimates for. Does this make sense? I'm going to go through an example, so hopefully that'll clear it up a little bit. But okay. So let's go through an example of what this would look like. This algorithm is called DQN, by the way. So as per normal, we're going to follow an entire episode, stopping at each state, right? Let's say we have a replay buffer already storing a bunch of values from previous episodes. And then let's say we have our neural networks here, our first Q network, so our first one to predict the Q values, and our target network in the gray, which will predict our help estimate returns. So as we just did previously, we're gonna pass our current state through the neural network to get our Q values. And these are gonna be just stored in the exact same fashion, right? Nothing changes here. Now we're gonna, again, as per normal, we're gonna take an action using our newly predicted Q values. This action is gonna be taken following the epsilon greedy policy, and will then receive a reward based on our action we just took. Nothing changes here. Okay, now that we have the state we started at, the action we took, the reward in the state S prime that we ended up at, we can add this to the replay buffer, right? That's all I've just added here. Okay, now we're gonna randomly pick rows from the replay buffer to serve as the training batch, right? So if you recall in our previous version of this algorithm, we had basically just went right into updating the neural network. Now instead of doing that, we're gonna first find the batch, calculate a few things that we need, and then train the neural network on the entire like batch result. Okay. So this is what our batch looks like. For each row, we're gonna calculate the expected return using the target network. This is basically the same step that we did in our previous version of the algorithm, except now we're gonna use our second neural network, the target network, to estimate the expected return. Okay, and this is the exact same formula as before. Nothing changes with this formula, right? We're just going to do that for every single row in our batch. So if it looks like this, I'm just going to kind of slide through this, but yeah, we're just updating the return for every single row in this batch. Okay, now we're going to find what Q of S comma A should be. Again, this is a step we did previously, because we want this Q of S comma A to be able to predict G really, really well. So we're going to find what Q of S comma A is, again, by just passing S through our Q network, right? Again, just flying through this. Yeah, if we were to just get these values, this is what Q of S comma A would be. Okay. Any questions so far on anything I've done till then? Okay. So now that we have this, we're just going to compute our loss, right? Our loss is, again, it's just going to be the MSE loss, the same loss we had in our previous version, only we're just going to average it across the batch, right? So if we have 4 items in the batch, we're going to compute the MSE loss between these guys, these guys, these guys, and then these guys, and then divided by 4 to average them, right? And this loss is then going to be used to update our Q network, okay? So this step, this update step for the Q network is going to happen every single time. However, for the target network, let's say we want to update it every 10 or 15 steps. So every single time the Q network will be updated, but only every 10 or 15 steps will the target network be updated. And if this was that 10th or 15th step that we would choose to update the target network, we backpropagate the same loss. What's up?
So you update like the main two network every time step?
Yes.
Isn't that, don't you end up sampling earlier like steps that happen earlier in your episodes? Like are those disproportionately represented?
Yeah, it's a good question. And the answer is not exactly. Because if you'll notice, the value G and Q of S comma A, these aren't getting stored. There's a reason we calculate these in real time. And that's because our neural network has changed. The only thing we store is this history, right? This is just, these 4 values just represent a decision that we've made. So this value of G, after we've done this update, could be something completely different because we've updated our neural network, right? So, right, because G relies on, if we go back a few slides, G relies on Q of S prime A prime, and that's being predicted by our target network. So maybe like if we come back to this row, like let's say, I don't know, 5 or 10, 15 15 episodes later, we could get a completely different estimate of G. Does that make sense? Cool. Any other questions? Cool. Okay. So yeah, we're gonna backpropagate this loss. And yeah, repeat basically this step until the episode is done, right? And then as before, we're gonna repeat every single time, then for multiple episodes until eventually your networks will converge to something that represents, you know, accurately predicting all possible Q values. Does anyone have any questions overall with this algorithm? Cool. So DQN is a pretty popular algorithm. Yeah, and hopefully you've seen that if you know how Q learning works, it's not that many steps further. So yeah, let's just to kind of represent where we are. I put up a similar figure at the end of our last lecture, right? Where we're currently in the family of value-based algorithms. We saw Monte Carlo as an algorithm. And this one, TD, it's estimating our return instead of actually calculating our return like Monte Carlo does. And again, for more information on either of those, last lecture should be up. So yeah, just check those out. But yeah, let's keep moving. Now we're going to get into a policy-based algorithm. So this algorithm is going to try to find an optimal policy. And just as a quick refresher, a policy is some function that tells the agent what action to take based on the state they're in. So if our ultimate goal, right, is to maximize our cumulative reward or maximize our return, this is basically a way of going about that. It's a more direct way than our value-based approaches. And because if we have an optimal policy, that means we have some function that tells us exactly what to do at any given state we're in. So just by following that, we should be maximizing our cumulative reward. Yeah. So we're going to be working with stochastic policies, which means that instead of like being a direct mapping between any state and action pair, every state will map to a probability distribution that you would then sample an action from, right? So if our state is here, this gray circle, this is what a policy could look like, where for every possible action, we have some probability that we would then use to sample an action from. So most of the time, if we ended up here with this policy, we would pick the action to move to the right, to move east, if you will. But sometimes we could get the other actions as well. So how do we represent a policy like this? Well, as you can probably guess, we can use a neural network to represent this policy. If we just pass the state in, just like we did with our Q networks in a few slides ago, we can have each value, each value in the output be some probability of taking any possible action. So like, look how this like corresponds, for example, right? You have your 0.05, which represents the 0.05 probability of the agent deciding to move up, a 0.4 probability of the agent deciding to move down, 0.45 of the agent deciding to move right, 0.1 of the agent deciding to move left. So yeah, this mapping is something I picked, arbitrary. You could pick something different, but it's just, yeah, important that you stick with it so it makes sense. So yeah, you can see how this might change for multiple states, right? So if you were to keep following this policy, you would, if it's really optimal, you would, get to the goal, get to the terminal state while maximizing as much reward as you can. So that raises a pretty natural question. How do we actually train this policy network, right? And the way we can kind of think about this is that we want the model to learn actions that lead to higher rewards, right? So we know what the return is, right? We know how to represent G, right, as our return. So in other words, basically we're trying to maximize G, right? This should be pretty intuitive, right? This is what we want our policy to do. So does that mean that we can take the negation of G at any given step and attempt to minimize it to train our policy network? And the actual answer to that, it's actually much closer than you might think to just doing that pretty simply. So, but there's a few more things that we need to do. First, just to reiterate, this is how we would estimate G, right? This is the same exact rule that I've probably shown you a bunch of times by now, right? We're just estimating the general return as the immediate rewards you get plus the value of the next state. So the expected return of the next state you would go after taking this action A. And this value is discounted by this discount factor. And we're just using discount factor of 1, as I've said before. But it turns out we can just use this exact same formula. But we're not quite there yet. So if we just negate this and attempt to minimize it, which is basically equivalent to maximizing positive G, right? That's intuitively what we want. But we can't exactly use that as a loss. And the reason for that is because G is relative. What that means is that your value of G, your return, it depends on the state with which you're calculating return from, right? This is just by definition. What that means is that states closer to the terminal state will generally have smaller returns than states further away. Does that make sense to everyone? That should be a pretty intuitive concept, hopefully. But what that means is that the model can't really tell the difference if you were to just use G just as itself. The model can't tell the difference between which state that return is referring to, right? If you were to give the model a return of 5 and ask it to learn from that, how is it going to know which state it's referring to? If you were at state, if you're at the state right before the terminal state, a return of 5 could be spectacular, but you just don't know. So what I'm basically trying to get at is that we want to normalize G, and we want to normalize our expected return so it has meaning irrespective of the state we're currently at. And the way to do this is what's called an advantage. And what this means is that we're subtracting the return we get from the state by the expected return of the state. So let me just clear this up. So we have G, which is in all intents and purposes, this is the return we're getting. We're estimating this using our TD rule, right? Which is a smoother way than to actually get the actual return, as I talked about in the last lecture. And we're subtracting this by the expected return of that state. So just to clear this up again, G, right? This reward plus gamma of V of S prime, that is our estimated return factoring in that we just took this action, right? Whereas V of S is going to be our estimated return irrespective of the action we just took. Does that make sense? It's an important distinction because I know these are really similar concepts, but this value G, it could be different depending on whatever action you just took, because it depends on the value of the state you end up at. It's not necessarily going to be equivalent to the expected return of this state. Remember that these value estimates, they're not optimal yet, right? We're currently in the training process. So this is a way to estimate based on our best knowledge, based on our best guess, how good is the action we just took? Does that make sense, that idea? Cool. So with this advantage, we're effectively scoring our return relative to how good we expect it to be, right? And that's going to depend on the action. Yeah.
So bigger the advantage, the worse.
The bigger the advantage, the better it is. But recall how a loss works in machine learning, right? We want to minimize it, right? That's how backpropagation is set up with gradient descent. So if we give it like, I don't know, like let's say our advantage is 5, right? We could negate it and then train and pass that to the model so that the model will hope to minimize it further, which corresponds in effect, in practicality, to a larger advantage. Does that make sense?
Yeah, so like the closer V of S is to G, the smaller the advantage is.
Yes, smaller the magnitude of the advantages.
Okay.
Yeah. Yeah. And that's basically what I'm getting at. Yeah. This advantage is normalized around 0 by definition, right? If we take the action expected of us, right? If we take an action that corresponds to how good we expect that state in particular to be, our advantage is going to be 0, right? We've done average, right? We could also do worse by taking a worse action that leads to a worse V of S prime, or we could do better by taking a better action that leads to a better V of S prime, right? So this advantage is equivalent to our return. It's just normalized around 0, right? So this is something our model can understand because this advantage, since it's normalized around 0, it doesn't depend on the state that it's referring to. So this is something we can pass to the model. Any other questions? Yeah.
Are you also learning G or just learning V of S?
Sorry?
Are you also like trying to learn what G is?
Yeah, we're doing both effectively. Yeah. Yeah. I'm gonna get into it, but yeah, these guys they're gonna start off, yeah, because we have random weights in a neural network. They're gonna start off being completely different, but they'll eventually converge. Our hope is that they'll eventually converge to something that makes sense. Good question. Any other questions? Cool. Just gonna move forward. So, yeah, that since we're using V of S, how do we find it, right? I've in the last lecture, I talked about how we could represent V of S with a value table or a value function, but recall that we're dealing with continuous states, right? A value table won't exactly work. So the solution is to use another neural network that learns to estimate V of S, right? And we can just call this a value network. It's going to be trained in a very similar way to how our Q network was trained with DQN, right? So this could be trained simultaneously with a policy network. So the policy network is a neural network that's used to output that probability distribution for any possible action. So the idea is that we have both of these networks that are trained simultaneously, but like with different losses. And ideally, they both help each other and converge to a really good strategy for the agent, right? And to solve the issue of batches, we can use the same replay buffer that I just discussed previously. So this family of algorithms is called actor critic. So let's just get into it. Again, as per usual, we're going to follow an entire episode with this algorithm, stopping at each state, right? So let's say we've accumulated our replay buffer here, and we're currently at the beginning of a new episode in the top left, where we normally start, right? Now we're going to get the policy for this state by passing it through the policy network, right? What this means is that we're going to pass, just as I said, we have this state 0, we're at state 0, 0. We're going to pass it through the policy network, get our probability distribution, right? And we know what each of these values represent, so just match it up. Now we're going to use this probability distribution to sample an action and then receive a reward effectively. Right, so let's say, based on this policy, I've chosen to move in the direction of the 0.45, and I've gone to the right, taken a reward of -1. Okay, now we're gonna add the pair SA or S prime to the replay buffer. These steps are basically the exact same as the ones we did in DQN, right? Same exact idea. The replay buffer served the exact same purpose. Since we just have different neural networks, we just have different ways of getting those values. That's the only distinction so far. So again, as before, we're going to randomly pick rows from the replay buffer to serve as our training batch, right? And we're going to add more values to these. So let's first try to train the value network. What we need for that is the value of each state in our batch, as well as what we expect the return to be. So we're first going to calculate the expected return, and that's going to be this reward plus gamma times V of S prime. Same exact formula as the one I had a few slides ago. So if we just go ahead and calculate that, that's going to be -1 plus V of S prime. So if we pass S prime into our value network, we're gonna get -2. Again, let's just say that's what we've got. So this is what our return would come out to be, -3. Does this make sense? Cool. So yeah, just doing the same exact thing for the next value, for the next row in our batch, I guess. Now that we have that, we now need to calculate V of S, right? The idea is that V of S should be really good at predicting G. It's the same exact concept of our Q network, right? We want our Q values to accurately predict our returns. Here, we're doing the same thing. We want our values to accurately predict our returns. So, let's say we've passed our first state 1, 2 into our value network and got a prediction of -2, right? And done the same thing for this. Now we have what we need to compute loss, right? We have our prediction, our V of S. We have our ground truth, if you will. We have what it should be. So we're just gonna compute MSE loss between these, right? Same exact formula that I've done with our Q table. And that's just gonna be this minus this squared plus this minus this squared divided by 2 to average. And we're just gonna take this loss and backpropagate it through our value network, right? So we're effectively training our value network to better predict our V of S. Does this make sense? Cool. So we're done training our value network for this step. We can basically set it aside. So what's left is to train our policy network. So we need a few more things to be able to train that. The first thing we need is for each row, we need to find out that the probability of each action being selected, right? So we need to find the probability that from state S, taking action A, we need to find that probability that happened. So that can be done by passing our state 1, 2 to the policy network and looking up the corresponding output that we care about that corresponds with action north, right? Moving up, for example. And let's just say that's -0.2, right? We can do the same exact thing for the bottom row as well in the batch. So now that we have these, as I said, we can't train directly on the returns, right? We need to convert them to advantages first, so they actually have meaning. And we can just do that. We don't need to use a neural network or anything for that. We can just do it by using the values we've already computed, right? We have G, we have V of S. So that value is just going to be -3 minus -2, which is -1. Same thing for our second item in the batch. Now that we have our advantages and we have our probability, we can then multiply the probability of each action being selected by that advantage and use that as the loss. So the probability is kind of acting as a weight to the advantage. The reason for that is because, again, our policy network outputs the distribution, right? Just because from state S, we took this action of moving north, just because we did that doesn't mean that we were always going to do that, right? Because it's a distribution. We could have taken a different action, depending on the probability, right? Because it's random. Let's say, to make it more clear, let's say if we're at a particular state and the policy network outputs the action moving south of 0.01, right? There's still a chance we could take that action. So let's say we did, right? And it came out to a completely horrible advantage. It came out to horrible performance overall for that episode, right? But remember, just because that action, that probability of 0.01, just because that causes us to take that action and suffer those horrible losses, doesn't mean that should affect our policy network a lot. Does that make sense? Because most of the time we won't take that action. Most of the time we might have taken another action considering this probability was 0.01. So this probability of each action being selected kind of serves as an importance check of how likely that action being taken actually was. And as a result, how much that result should matter to the neural network. Does that make sense? Cool. Okay. So yeah, that basically is the last thing we need. We're going to multiply this probability by the advantage for each row. And again, average these two to use as our overall loss. And notice I'm negating the advantage here. I'm using +1 instead of our actual advantage of -1. So this loss will then be backpropagated through the policy network with the hope that, it'll learn and eventually get better. So yeah, that wraps up actor critic. And again, as per usual, we're going to repeat this for every step until the episode is done, and then for multiple episodes on top of that, until hopefully these networks correspond, or sorry, these networks converge to something resembling the optimal policy and values. Cool. Before I move forward, any questions on that at all? I know it was a lot. Cool. Okay. So that pretty much wraps up these two algorithms. So just to kind of recap, we looked at DQN, which is a version of Q learning that uses neural networks, and it's in this family of value-based TD algorithms. And actor critic, which is a policy-based algorithm that also uses TD, but yeah, as I said, it's policy-based. It hopes to find a policy for the yeah, it hopes to find a policy for an environment. So yeah, that wraps up today's lecture. Yeah, thank you for coming, and yeah, stay after for questions, I guess. Yeah. Do I like stop the recording?
Any
All right.
questions?
Let me see.
Chat.
Thank you. Nice. Okay, let me just stop the recording.